Hi there, welcome to this video on design patterns. In this video, we will look at all the different design patterns that are present in object-oriented programming. We would really focus on the gang of 4 design patterns, but we would take a completely different perspective on it. We would not really look into code, but we actually will look into real-world examples. So we'll take each pattern and we'll compare it with a real-world example. Let's just take an example. Let's say I want to talk about a mediator pattern. A mediator pattern, the real comparable real world example to that is an air traffic controller. You have about, let's say, 50 different airplanes flying in different places in India. Think how complex it would be if they have to talk to each other to decide the route they need to take, to decide when they have to land at a particular airport. That's where the air traffic controller comes into picture. The air traffic controller acts as the mediator. All the flights would talk to the air traffic controller, and the air traffic controller would guide the flights as to which route they can take, when they can start flying, when they can land, and all this kind of stuff. So we would use real world scenarios like this to understand all the design patterns. Design patterns in general are classified into 3: creational, behavioral, and structural. Those are the 3 that are highlighted on the screen right now: creational, behavioral, and structural. Creational design patterns deal with creation of objects, how you can create objects, how you can efficiently create objects, what are the different patterns which are related to that. Those are what are the creational patterns. The behavioral patterns discuss the different objects and how they interact with each other. So these behavioral patterns are about the interactions between the objects. So about how an object talks to another object. The structural patterns are how the objects are composed. So is there an inheritance relationship between them? Is one object present in another object? One object composed in another object. So this is really the structure of a object. So how is the structure of the object, and what are, like, is there an inheritance relationship? What are the interfaces which are present? So those are the different things which would come under the structural design patterns. So let's get started. We would get started with the creational design patterns. The most important of the creational design patterns are highlighted in the screen right now. Those are prototype, builder, singleton, and factory. There are multiple variations of the factory pattern: abstract factory, factory method, and other stuff. Let's get started with the prototype pattern. So the prototype is the first of the creational patterns. So what is prototype pattern? What is it related to? So in summary, prototype pattern can be defined as a fully initialized instance to be copied or cloned. Okay, sounds complicated. Let's make it simple. Let's take the example of a chess game. In the chess game, we have an initial setup. There's a particular place where the rooks have to be. There is a particular place where the bishops have to be, king, queen, and the knights, and also the pawns. So there is a specific initial setup that is there for the chess game. So creating this setup in, let's say, in a class, in an object, would involve some effort. So a chess game, let's say I'm implementing a program for a chess game. In that kind of a game, I can store the initial setup of the chess game as a prototype. So I can have the initial setup as a prototype, and whenever somebody asks for a new game, I can clone this and give it back. So this is a prototype pattern. So a prototype pattern is used to create a copy of a fully initialized instance. So that's the prototype pattern. So you, just like the chess game where you, instead of doing the initial setup again and again, we reuse the initial setup. There might be other places while we are doing software where the initial creation of an object might be very time consuming. I might need to talk to an interface and get something. In these kind of situations, I would go for a prototype pattern. I would do the initialization of the object once, and later I can use the object for cloning. So in such kind of instances where the setup of an object involves some amount of effort, you can create a prototype of that particular object, and whenever a new object needs to be created, you can clone the existing prototype and keep returning it back. So that's the prototype pattern. Now let's go on to the next one. The next one is the builder pattern. So the builder pattern is basically used when there is a complex object structure. Like in object-oriented programming, when we are using domain-driven design or something of that kind, we have a composite structure of objects. So if, let's say, I have a multi-course dinner, a multi-course dinner would contain a drink, a starters, main course, and a dessert. So these are the different parts of the class for multi-course dinner. So the creation of this particular class would be really complicated. So in those kind of situations, we would go for a builder. So we would try and separate object construction from its representation. The representation of this dinner is that it has a drink, it has starters, starters might have multiple options, and a main course and a dessert. However, to construct this, we would really provide a simple interface. So somebody who wants to take a multi-course dinner would just say, I want this, this, and this, and we would take care of constructing the entire objects for that. So we are separating the creation from the internal representation. Even though the internal representation is complex, we are providing a easy interface to the outside world, and that's where the builder pattern comes in. So the builder pattern comes in when we want to hide a complex internal structure from somebody who's trying to use the interface to create an object. So separates object construction from its representation. So that's basically what the builder pattern is all about. Let's now move on to the next one, which is the Singleton pattern. Singleton pattern is almost the simplest of all the design patterns. In a Singleton pattern, the most important thing is the fact that you can only have one instance of that particular class. So there are a lot of circumstances where you would want just one instance of a particular class. Let's take a real example, a president of a country. There can only be one president in a country. So that's a good example for a singleton. I mean, if you look at Java, the system class is a good example of a singleton. A Java JVM would run only on one system. So system should be a singleton. You cannot have multiple systems. So this is a very good example of a singleton. So singleton is something which there can only be one instance of. The only thing which you need to be really careful about is that when you have multiple JVMs running the same program, then you would have one instance per JVM. So even though we call it a singleton, it's when the program runs on multiple JVMs, it can still have multiple instances in these different JVMs. So you'd have one instance in each of these JVMs. And also there are a few things that you need to be concerned about implementing a singleton. The first one is you should definitely make the constructor private. So for a singleton class, it's better to make the constructor private. If you are interested in how to implement a singleton, good singleton, you can look up effective Java. There's a very good way of implementing a singleton using enum. However, if you're using JEE 7, then you don't even need to worry about implementing a singleton. It has a @singleton annotation. So there's an annotation called @singleton in JEE 7, which you put on a class @singleton. That's it. You have a singleton class. You can also have additional options to customize it, like at startup, at post construct. What do you want to do during the initialization goes into the method which is annotated with at post construct. At startup indicates if you'd want to load this singleton at the startup. Otherwise, it would only be loaded when somebody uses the singleton. And also, you can have relationship between different singleton objects. So you want a singleton object A initialized first, and then B, and then C. And the depends on can be used to create these relationships. Not really important, but if you are using JE7, probably you can look this up more. And also, singleton objects should be avoided as much as possible because they make code very difficult to unit test. So if you use singletons, then your code becomes very difficult to unit test. So you should try and avoid singletons as much as possible. One another good good place where you have singletons is Spring. In Spring, almost all the beans that you create are singleton by default. So that's very good to know. So there you go. That's the singleton pattern. In a singleton pattern, basically you have just one instance of a class per JVM. A good example is java.lang.system, or all the beans when you are initializing them using Spring. And also remember to have a private constructor, and you can look up effective Java for how you can use a singleton, how you can create a singleton using an enum. It's quite simple actually. Now let's move on to the next creational pattern. The next pattern we would be talking about is the factory pattern. We would talk about a specific instance of a factory pattern called the factory method. So we'll do a change here and we'll look at a piece of code to understand it better. So what you're looking on the screen is a simple example of a factory method. So you have a person factory. So this is the entire code highlighted. So you have a person factory where there's a getPerson method, and it's accepting a parameter called gender. Based on the value of gender, where if the gender is M, it's creating a male object, else it's creating a female object. So all the creation, the instantiation logic for the male and female, for the person object, is present inside this particular factory. What this helps is in reuse of it. So once I have a factory, I can use it anyway to create different persons. I can have male, female, different, later if I want to add more stuff, yeah. So if you, in other circumstances where you have different varieties of things to be created, this helps you in making it much more extensible. And also the other important thing is the user of the getPerson method doesn't know that there's a male class or a female class present. He only knows about the person class. So whichever method calls the getPerson method knows that there's something called a person class, but it doesn't know the existence of a male and a female. So you can even hide the existence of certain classes and in there. So the factory pattern is, this factory method pattern helps us to create instances of a single family of objects, and it can separate the instantiation, and also it can separate the existence of this object, so that tomorrow I want to change this male object to something else, I want to create a new class, I can do that without affecting the other methods which are using this. So that's the factory pattern, factory method pattern, to be specific. So now that we looked at the different creational design patterns, we would move on to the other stuff. We would move on to the structural design patterns. So what you are seeing on the screen right now are some of the structural design patterns. The important ones are proxy, decorator, facade, adapter, and flyweight. Let's take them one by one. Proxy. What's the proxy pattern? So a proxy is something, is an object representing another object. So what's a proxy? A proxy is an object representing another object. Let's take a real world example. So let's say I want to buy something at a shop. So what do? I take my debit card or a credit card and swipe it. but actually where does the real amount go from? It's from my bank account or from my current account or a savings account. So this credit card which I use or a debit card which I use is really a proxy for the bank account. So I'm not really using the bank account, but I'm using a proxy of the bank account. So this is exactly the pattern of proxy. So this is useful. I mean, in the EJB world, there is something called a remote object and a home object. A remote object represents a class which exists somewhere on a different application server or a different container, and you use the home object to talk to it. So home object acts as a proxy. So use the home object as a proxy to talk to the remote object. So this proxy is a very simple pattern where you would start talking to something on a network. Let's say there is something present on a network and you want to talk to it. So what we do is we create a proxy, and the proxy talks to the real object, whereas the program would start talking to the proxy, so that the program doesn't know the existence of the remote thing. So program thinks that the proxy is here, proxy is local, but actually the proxy is really talking to something on the network, something remote as well. So that's basically the proxy pattern. The proxy pattern is basically an object which is actually acting. It's an imposter. It's an object which is acting like another object. It's not the real object, but it's like a proxy of another object. So it hides the complexity of different things. So that's the proxy pattern. Now let's look at the next one, which is the decorator pattern. Decorator pattern is little complex to understand first, but let's try and make it easy. If you look at the definition, it says add responsibility to objects dynamically. Probably at a first glance, you would not understand it a lot. I would take an example. Let's say there are 10 different types of pizza. So I have a chicken pizza, I have a vegetarian pizza, I have other pepperoni pizza, whatever pizzas that they are. There are 10 different types of pizzas, and the new company has 10 different classes. Let's say I have a program with 10 classes representing all these pizzas, and now I would want to add 3 different toppings for each one of these pizzas. So I have to create a program where I would need to extend the program so that I can offer these pizzas with 3 different toppings. So let's say the toppings are, let's say, a pineapple topping or something else. So if I have to really follow the inheritance structure, then I would end up making 30 classes. So I take a vegetarian pizza, I take each 3 of the toppings and make a class out of it. So I would have a pineapple topping, a vegetarian pizza, and let's say there is some other fruit topping. Then I have to create another fruit topping vegetarian pizza. So I would need to create 30 different classes. And imagine if there are different sizes of topping. I want this topping in small quantity, this topping in medium quantity. Then we are talking about a number of variety of classes that are created. So that would really create a very complex inheritance hierarchy. So the decorator pattern tries to handle that more efficiently by making the toppings as a dynamic thing. So what we do is we decorate the pizza. We kind of put around the pizza a topping. So what we would do is we would create a new topping and pass pizza as the parameter to it. So that's the decorator pattern. So we don't really create a new type of pizza for the toppings, but we take an existing pizza and put a topping on top of it. So the topping, you can pass any of the 10 types of pizza to this particular toppings thing, and it would add the topping on top of it. This is also similar to adding a discount on an order. So let's say there's a Black Friday sale, and there's an order, and I would want to add a discount on top of it. So the discount is added as a decoration on top of the order. A good example of decorator pattern in Java is the Java IO. So in Java IO, this is how you would create objects. So you would create a file input stream and then pass it to the buffered input stream. Then it would make sure that the buffered input stream can work on any input stream. It doesn't have to be a file input stream. It can be any other input stream, and still the buffered input stream would be able to decorate it and give buffered functionality to it. So this is to read a file entirely. This is to read a file in a buffered way. So this buffered input stream can talk to any of the input streams. It doesn't have to be file input stream. It can be any other file input stream, and the buffered input stream adds the capability of reading everything in a buffered way. And the line number input stream is on top of the buffered input stream. So to any buffered input stream, you can add the functionality of reading and of getting the line number of what line number are you reading by adding another decoration called line number input stream. That's why you would see that the Java IO, the creation of the classes is little complex. So you need to understand the entire structure, and only then you would be able to create the object. So there is a complexity in creating objects. So whenever you go for a decorator pattern, one of the disadvantages is creating the entire sequence. Since it's dynamic, it's a little complex. There isn't a single class called line buffered file input stream. You have to create a file input stream, pass it to the buffered input stream constructor, and that is passed to the line number input stream constructor. So there is a complexity in creating objects. Similar thing with the pizzas as well. So instead of saying new pineapple topping vegetable pizza, you would say new pineapple topping and pass an instance of the vegetable pizza class to it. So there is a small drawback to the decorator, but it helps in adding dynamic functionality to existing objects. So that's the decorator pattern. And next we would move on to another pattern called the facade pattern. A facade pattern is, if you look at the definition, it's a single class that represents the entire subsystem. Okay. Sounds complex. So a good examples of facade pattern in the real world is event managers. So let's say I want to organize an event, and I would have to take care of a lot of things. So I have to take care of the decoration of I have to book a place, I have to take care of the decoration of the place, make sure that the right food is available, right drinks are available, send the invitations, arrange for a music trip, and all this kind of stuff. So instead of doing all this myself, I can go through an event manager. The event manager would act as the facade. He would actually act as the facade, and he would take care of arranging for a decoration, food, invitations, music group. So all that I need to do is tell the event manager I need A, B, C, D, and he takes care of arranging that. So that's basically a facade. So event manager is a facade. So I just need to call the facade, and the facade takes care of doing all the steps that are involved. So event managers are really good examples of facade. A technical example would be let's say I want to buy a book online. So I want to buy a book online. There are different steps. So let's say I have to check whether there is a stock available, and if there is available, I have to reserve the book. Then I have to make the payment, update stock so that the book quantity is reduced, availability quantity is reduced, and then generate the invoice. All these are the different steps that are needed. However, when I look at it from the UI perspective, all there is a single click. So when I make a single click on the UI, it goes to the web layer, and the web layer invokes a method on the business layer. So the business layer is where the facade would be, and the business layer offers a facade which does all these steps. So the facade pattern is very useful in all these kind of scenarios. A facade pattern separates the entire steps that are there in a subsystem from the systems which are using it. So even though there are multiple steps, the facade pattern would make it seem as if there is only one step available, one step that is needed. And when I look at the advantages of facade pattern, the first advantage is reduced network calls. Let's say the let's say the business layer is deployed on a different application server. Then if there is no facade, then I have to, from the UI, I have to make multiple calls, 1, 2, 3, 4, maybe 5, 6. So facade reduces the number of calls over the network. The next thing is reduced coupling, because the web layer needs to know only about the facade. It doesn't need to know anything about the subsystems. So these subsystems can be changed without worrying about how it would affect the web layer. The only thing which would need to change would be the facade. So that's one advantage of facade. It reduces the coupling between the web layer and the backend, and also it helps in establishing the transaction boundary. So let's say while making a payment there is a failure, I have to make sure that this is reversed. So this reserving of the book is reversed. So things like this are so the facade kinds of forms the transaction boundary. So if any of these steps fails, the previous steps are rolled back. So facade is also good in establishing a boundary, transaction boundary. So that's the facade pattern for use. Facade pattern is really useful, very frequently used in web applications, in a lot of other applications as well. Next, we would talk about the adapter pattern. I mean, adapter pattern is quite simple. You have it's very similar to the power adapters. I am from India and I buy a mobile phone in here. I get a charger which works only in India. So what should I do if I go to US? What I do is I buy a adapter which can convert, which can take the input as which has input as whatever plug points that a power adapter in India has, and the output on the other side it can connect to a power plug in US. So that's the adapter pattern. It converts, matches interfaces of different classes. So I have two different classes which need to interact, but they're using two different interfaces. How do I connect them? So what I do is I create an adapter class in between them and help them talk to each other. So that's basically the adapter pattern. The next pattern we are going to talk about is the flyweight pattern. So what is a flyweight pattern? To understand it, let's take a real world example. In the earlier days, we used to have this public switch telephone network. There are about 5-6 connections which might be present, but these are used to serve all the people who live in a particular locality. And based on whichever person, like when I lift the phone, for me it's as if I have a public, I mean I have a connection for my own, but it's actually not. There are only a limited set of connections, and the public switch telephone network makes sure that those are properly used. So that's exactly the flyweight pattern. What we would do is certain times it's not needed to create separate instances of objects. So if there are 1,000 instances of objects, that 1,000 instances of objects that needs to be created, then it's a lot of objects. What we can do is, instead of creating a new instance of the object each time, we would set the right values in the object and then do the functionality that is needed, and then again set the values and do the functionality without creating a new object. So we would try and reuse the objects as much as possible. So you would create a fixed instance of objects and try and use them directly. Next, we would move on to the behavioral patterns. The behavioral patterns, as we discussed earlier, have are about the behavior of the objects. That's basically the different interactions that are present inside an object. The first behavioral pattern that we would look at is the chain of responsibility pattern. So let's get started with the chain of responsibility pattern. So a chain of responsibility pattern is defined as a way of passing a request between a chain of objects. So a way of passing a request between a chain of objects. Let's take a loan approval process. So a loan approval process typically goes through several steps. First, it goes to the loan clerk, and the loan clerk checks if he has all the different things that are needed. and if they are needed, but let's say the amount of loan which needs to be approved is very high, then he would send it to the manager's approval. If the manager looks at it and he feels the amount is something which he can approve, he would approve it. So this is a sequence of chain. So the loan request is going to first the officer who is designated, and then his manager, and if that manager cannot handle it, he would send it to the loan manager. He would send it to his manager. So that's basically the chain of responsibility. So you would have a chain of objects. So the chain of objects here are a clerk, his manager, and the manager of the manager, and the request is the loan request. So this loan request passes through these different objects until it finds somebody who can actually accept it or reject it. So this is basically the chain of responsibility. A good example of chain of responsibility pattern is how exception handling is done in programming. Let's say a method 1 calls method 2 and method 2 calls method 3, and an exception happens in method 3. First, method 3 checks if there is a try catch block there. So if there's a catch for that particular exception in method 3, then it would be handled right then and there. If it's not there, then it would go to the calling method of method 3, which is method 2. And in method 2, we would check if there's an exception handling if for that particular exception. If not, it would go on to method 1. So this is a very good example for chain of responsibility. Exception handling in actually not just Java, in most of the programming languages would work the same way. If a method doesn't handle the exception, it would be sent to the calling method of that method, and so on. So that's a good example of chain of responsibility. Another good example of chain of responsibility is the logger pattern. So when we define a logger, we define a number of handlers. So based on the log level and the type of class which is causing it, the respective handlers are invoked. So when I log something, it would pass through all the handlers which are registered, and they see if they can log that particular message. So this is also a good example of the chain of responsibility pattern. So to summarize, the chain of responsibility pattern is a way of passing a request between a chain of objects. So you have a chain of objects and the request passes through them until it can find somebody who can handle that particular request. So again, this ensures that there is very less coupling. So the request doesn't know about anything about the objects. So the only thing we do is pass the request to different objects. The request has no idea about who is handling it at all. So, and it's easy to add and remove objects from the chain. So you, instead of having 3 objects in the chain, you can have 4 or 5 very easily. So that's the chain of responsibility pattern. Next, we would discuss about the Iterator pattern. What is the Iterator pattern? Sequentially access the elements in a collection. That's basically an Iterator pattern. Iterator pattern is quite commonly used. A good example of an Iterator pattern is I have a TV remote and I press the next button, it goes to the next channel. I press the previous button, it goes to the previous channel. And you can keep pressing the next button to loop through all the different channels. Without knowing how the remote works, I can just using the next button and the previous buttons, I can iterate through the list. That's basically the Iterator pattern. So if let's say I have an array or an array list, a collection. So the Iterator pattern is commonly implemented in the collections so that you can loop through the list. So it doesn't matter if it's a array list or an array. The internal representation doesn't matter. So how the different objects are stored in an array list doesn't really matter. How it's stored in an array doesn't really matter. How it's stored in a hash map doesn't really matter. All that I do is I get an iterator and I keep calling next and the previous methods on it, and I would get the next and the previous objects. This helps in making sure that the internal representation of the array list or the hash map, the outside world doesn't need to know about it. So if I want to use a hash map and I want to loop through everything inside the hash map, which is not what we would usually do. We would get it through a key. Let's take the example of an array list. If I have an array list and I want to loop through it, all that I need to do is get the iterator and rotate around it. I mean, do a next. Now you can use the enhanced for loop for doing it, but let's say there are other collections where the iterator is needed. So in those iterator collections, the iterator helps us to loop around it and get the appropriate details. And the object which is trying to loop around it doesn't need to know about the internal representation of the object which it's looping around. So that's the iterator pattern. Iterator pattern is quite a common one. It's frequently implemented. We would now look at the state pattern. The definition looks little complex. Alter a state's object behavior when its state changes. Okay, looks little complex. Let's take an example. Let's say I have a fan wall control. So I have a fan wall control where there are 3 different levels. So I have level 1, level 2, level 3 and level 0. Level 0 is when nothing happens. I can switch it to level 0. Fan rotates at certain speed. Level 2 rotates faster. Level 3 it rotates even faster. So these are the 3 control levels. I can implement this in this way. If level is equal to 1, then speed is equal to this much. Else if level is equal to 2, then speed is equal to this much. If level is equal to 3, speed is this much. So this is one way of implementing this particular logic of the fan wall control. The other way of doing it is by representing each of the states as each of these levels. So level 1, level 2, level 3 as different states. So level 1 can be a state, level 2 can be another state, level 3 can be another state. And when the switch is called, when the knob is turned, then the level 1, a method is called on level 1 which would switch it to level 2. So here we are representing each of the levels, which level a particular which level the control is in a class, and that is what is called the state pattern. Let's look at a code example. We have a speed level interface which has a rotate method, and the rotate method is on the fan wall control. So the rotate method, if we look at the states, can be off, speed level 1, speed level 2, speed level 3, and each of these is represented as a state. So these are the different states that this fan control can be, and these states are represented as different classes. And when the rotate method is called on off, then the state would change to speed level 1. If rotate method is called on speed level 1, it changes to speed level 2. When it's called on speed level 2, to speed level 3. When it's called on speed level 3, it goes back to off. So in this kind of way, if there's a new speed level that is added in, all that I need to do is, if I want to add a new level in, I don't need to touch the other classes. I just need to add another level here, and I can go ahead and use it. And let's see how it's being used. So all that we do is we make the speed level like as part of the fan wall control object. So this state, the speed level is this state. So the state is made part of the fan wall control, and it starts off, when in the constructor we would start off with the off level, and whenever there is a rotate method called, the rotate method is called on the speed wall control. So when the when a rotate is done on the fan wall control, the rotate method on the object on the state on the speed level is called, and it moves on to the next speed level. So that's basically the state pattern. This is where you take the state of an object, the current state of the object, and make it a class and make it part of the object where it needs to be present in. We would now talk about the strategy pattern. The strategy pattern is quite a simple design pattern. Let's say I want to sort a certain number of things. However, let's say this sorting algorithm which I want to use here, I'm not really confident about it. probably I would start off with a very simple implementation. I'll start off with a bubble sort, and at a later point in time I would want to switch on to some other strategy of doing it, some other algorithm. In that kind of situation, I use a strategy pattern. So basically what we do is we create a interface defining the we create a interface for this particular strategy, and we would create implementations of this, and the class which is using this strategy would use the interface, and we can change the implementation dynamically. So a good example is the comparator interface. In the comparator interface, you can implement the compare method. You can extend the comparator interface, implement the compare method, and you can use that to sort different things in an array list. So that's a very good example of a strategy pattern. Let's also look at a good code example. So here we go. We have an interface called sorter. Actually, it should be something like sortable. Sorter is not really a good name. So let's say it should be something of the kind. And I define a sort, and I pass the numbers, and it returns the sorted set of numbers. I have a bubble sort, implements the sortable, and ideally the implementation of bubble sort needs to go in here, but I'm not really implementing it here. Just a quick example. Or I can do a quick sort. So I can have this kind of stuff. However, let's look at where we are going to use it. Let's say there's a complex class which is using the sortable. So now all that I need to do is pass the sortable to the constructor. And how we do the sorting, it can either be bubble sort, it can be a quick sort. I can change that in here. So when I'm creating the class, I can either create it with quick sort, or I can create it with, let's say, bubble sort. And based on what I pass in, how the complex class behaves would be different. So we are abstracting how the sorting is done outside of the complex class, and this is an example of the strategy pattern. We are changing the algorithm dynamically. So based on what algorithm is passed to it, the way the objects are sorted in the complex class would be different. This is a very good example of the strategy pattern. The next pattern we would be looking at is the observer pattern. The observer pattern, if we look at the definition, it says a way of notifying a change to number of classes. There's a change in one object, and it needs to be notified to multiple different objects. So in those kind of situations, we go for the observer pattern. A good example is online bidding. When if I want to listen to an online bidding, I can register to it. So I can say I can place a bid and register to it. And whenever somebody new places a bid which is higher than what I placed, I would get a notification, and everybody else gets a notification too. That's a very good example of the observer pattern. So everybody who's bidding is observing the bid. Whenever there's a new bid, whenever there's a new bid, all the things which are listening are notified. So that's a very good example of the observer pattern. And actually the observer pattern is implemented by default in Java. It's in Java 7. There's a default implementation for the observer pattern. You can extend an class called observable. So whichever subject you would want to listen, so it can extend the class called observable, and all the other observing classes, so whichever classes want to do the which want to observe, can implement the observer interface, and they can register with the subject. So they implement the observer class, and you register them with the subject, and whenever there's a change in the subject, the observer would be notified. So the observer.notify method will be called to notify the observer. So the observer can take the necessary action. However, it's not a perfect implementation in Java because it's extending the observable class. It means the subject class cannot extend any other class, and that's quite a constraint because most of the classes that we use would have some kind of a superclass, and if I have to extend another class, probably it limits the usability of this built-in pattern in Java. Let's look at an example for the observer pattern. For those who don't know, Sachin is quite a famous cricket player, and there is a lot of people who are interested in knowing where Sachin hit century. So all these guys are Sachin fans. So these guys want to know when Sachin hits a century. So if you look at the Sachin century notifier class, there's a method called register. And whenever Sachin scores a century, you would all the fans would be informed that Sachin has scored a century. So, and whoever wants to listen it can call the register method and add himself. So you can look at it here. So the fan class would look something of this kind: Sachin fan and his name, and announce I am notified. So if you look at this, any number of fans can register. So I'm calling the register method on the notifier and registering to it. And once Sachin has scored a century, the notifier would call Sachin scored a century, and all these methods would be notified that all these listeners, all these classes would be notified that Sachin has scored a century. So this is a very good example of the observer pattern. One important thing to note here is I have not made use of any interfaces at all. I just wanted to keep it really simple. So in a real world implementation, you would have proper interfaces defined for a fan and also the notifier. So there would be interfaces defined on both the sides. So this is a simple example for a observer pattern. The next pattern that we would talk about is the visitor pattern. Visitor pattern is little complex to understand, but let's see if I can make it simple. Defines a new operation without changing the class. So you have, let's say I have a framework. I have a framework where there's a particular class defined. However, I want to give the users of the framework a way of adding new operations, new functionality onto this particular class. How do I do that? The obvious way would be through inheritance, but let's say there is no inheritance relationship, there is no ESA relationship. The option there is by using visitor pattern. So if I implement the visitor pattern, then the other classes can add operations to the existing class to do certain things, especially when there is a complex hierarchy of objects. A visitor pattern is really useful. A good example is how the operation of how a taxi company operates. A person calls a taxi company, he's now registered. So a person calls a taxi company, he's registered. Then the company dispatches the cab to him, and so the visitor is accepted. So now the visitor is accepted, and when I enter the taxi, I'm no longer in control of where I'm going. The visitor is no longer in the control. So the actual transporter, the real object takes control. So that's the taxi driver here. So that's the visitor pattern. Visitor pattern is more used to dynamically add new operations to a class without making modifications to the real class at all. The next example is a template method. A template method is usually used in places where there's a sequence of steps. Like let's say I want to do something with a file. I have to open a file, then perform the operation, then close the file. So these are predefined steps. So I can create a class with the predefined steps. So I can say, I can create a template method saying open the file, perform operation, and close the file. And you might want to do different operations, different write operations on the file. So all the other class, I can make the perform operation alone because I don't know how to perform the operation. The operation might be different. So in that cases, I can make the perform operation method abstract. So I can make the perform operation method abstract, and I can have the operations implement that particular method. So the template method would always call open the file, perform operation, and close the file. So perform operation is different. So the concrete classes can implement the perform operation method, thereby getting different operations. However, the outline remains the same. Open the file, perform operation, and close the file. That's an example of a template method. A good real life example would be to have like how we build a house plan. There's a template to a house plan. So there is already predefined set of steps. You have a floor plan, you have how the foundation, the framing, plumbing, wiring, everything is done in a floor plan. Like everything is already there. However, if you need to do a small customization, you just extend it and do that particular kind of customization. So if I want to add a wooden flooring or a carpet, I can do that. If I want to add an additional wing to the house, I can do that. I can paint a different color to the house. So those are specifics that can be changed. However, there's a template method which defines the entire thing. So that's the template method pattern. The other pattern, let's now look at the command pattern. Command pattern is another example where a command, a complete command is stored as an object. A good example for a command pattern is how things work in a restaurant. Let's say I want to go to a restaurant and order something. What I do is I give an order, the waiter notes down everything on a piece of order sheet. So he or she would take the order sheet and write down the list of things I have ordered in the order sheet. This order sheet is the order object. So now she takes it and gives it to the chef, and the chef knows how to execute whatever is there in the order. So that's basically the command pattern. So the command which is being executed here is the piece of sheet, the order sheet. So once a particular action happens, let's say there is a remote control and there are 10 different buttons on the remote control. What we would do is we would attach 10 different command objects to each of these 10 different buttons, and when the button is pressed, the execute method of that particular command is invoked, and that can decide what needs to be done. So the entire thing is encapsulated as a command. So that's the command pattern. A good example of a command pattern in Java is how the threads are implemented using the runnable interface. So all that you do is implement the runnable interface and implement the run method. So in the runnable interface, a thread implements the run method. Once you do that, you can call the start method on the thread, and it would start all the steps that are defined in that particular command object. That's the thread. So this is the command pattern. The next pattern we would be looking at is the memento pattern. A memento pattern is defined as capturing and restoring an object's internal state. Okay, let's make it simple. A memento pattern is used in situations where, for example, there's an undo redo operation. So in let's say Microsoft Word, I did something, I typed something, I want to do undo. I do a Control Z, so it goes back to the previous state. So the way memento object is memento pattern is implemented is by storing the state of the objects at different points. So what happens when I type a word? Microsoft Word would store the state of that particular thing in an object, and I type in something else. Again, a new object is created with the state at that particular point. When I do a Control Z, the object which was previously there, it would be restored. So this is how the memento pattern is implemented. For example, let's say I'm playing a game and I've crossed a particular stage in a level. I want to store that I want to make an intermediate save. That's where I can do a save. I can store the state of the object as it is right there. I mean, for example, serialization can be used. So I can use serialization to save the state of the object as it is right there. And once, let's say I go further and I fail, I can restore to this particular state from the serialization thing and go ahead and do start from there again. So this is basically the memento pattern. Basically, you make a few intermediate saves so that you can go back to that particular point. This is also similar to how save points are done in database. So in a transaction, you configure save points and you can roll back to those save points. So this is examples of the memento pattern. The last pattern which we would discuss here is the mediator pattern. A mediator pattern is used to simplify communication between a number of classes. Let's say there are, let's take the example of a air traffic controller. Let's say there are 100 flights flying, and if each flight talks to other and decides when to land and when to which route to take, then we would really have chaos. So that's where the air traffic controller comes in. The air traffic controller comes in, they decide, they talk to all the flights, and they suggest which routes to take. When do you do the landing? How do you do the takeoff? Which direction you do the takeoff? So all those things are decided by the air traffic controller. A good example also is the ESB. So instead of applications directly talking to each other, we use an enterprise service bus. All applications talk through the enterprise service bus, and the enterprise service bus kinds of becomes the center point through of communication. This is a good example of the mediator pattern. Okay, there you go. We looked at varied kinds of design patterns with examples. The focus for this video was not to really look at the code for this pattern, but was to just get a real world feel for them. What is a pattern? I mean, what does it do? Just what situation can I use a pattern? That's basically what we wanted to learn out of this video. It was not the idea of this video to be able to implement a pattern or something of that kind. Once you are able to recognize the situation when a pattern applies, at a later point in time when you want to go back and refer to the pattern, you can find the appropriate documentation for the pattern. But the most important thing for me is to identify the situation for the pattern. So when a situation happens, you should be able to think and say, okay, in this situation, this is a good pattern to take. So that's basically was the point for creating this video. If you like this video, like it, share it, subscribe to our channel. Thanks for watching.